Okay, we've been looking at binomial probability distributions. And the example I was giving was Kobe Bryant shooting free throws because we said, what's the probability of him making 3 out of 5 free throws? We knew exactly how many free throws he's going to shoot, and we were looking for the number of successes. But another situation is what we call a geometric situation. And if I to modify the Kobe Bryant situation, what if I were asking him to keep shooting free throws until he missed, or to keep shooting free throws until he made? Conceivably, that could go on for a very, very long time. Kobe Bryant, in particular, if I asked him to shoot free throws until he missed, he could get hot and hit 10, 20, 40 in a row, 50 in a row, and it could literally go on forever. Eventually, I'm sure he would miss. He wouldn't go on forever, but potentially it could happen. And that's the difference between a geometric one and a binomial. Binomial, we know exactly how many times this can happen. Geometric, we don't. Infinite number of trials is actually a possibility. So remember, a binomial, you had to check for the 4 conditions: binom, e, all. For geometric, we use the mnemonic device bits. Bits is a binary, again, 2 outcomes, success and failure. Makes the free throw, misses. Independent, one trial results does not influence another. So just because Kobe Bryant makes 1 free throw, his probability of success in the next free throw is not influenced by that. But the difference here is trials. This is the number of trials you're going to go until the first success occurs. And then success, each probability of success must be the same. So we do use the mnemonic device bits to help us remember that. So it's sort of like binomial for a binomial situation. So once again, a geometric random variable is what's the probability of a certain event happening until the very first success, until Kobe Bryant makes his makes a free throw or misses a free throw. Those kind of situations are geometric. We got to be able to distinguish between those that are geometric, those that are binomial, and those that are something else. So I'm going to give you some examples, and let's see if we can figure out the difference. So here's an example, and we got to determine if it's geometric or not. What if the question I asked is, how many times would you have to draw a card until you got an ace? Again, that conceivably could go on for a very long time. It wouldn't go infinite in this case because there's only 52 cards in the deck, but it could go on for a long time. We cannot tell you exactly how many trials it would take. So face value, it looks like a geometric because you can get an ace or not get an ace. The problem is that this one is not, the probabilities are not the same throughout the whole experiment. If I draw a card the first time and I don't get an ace, I'm going to draw another card. If I don't get an ace, I'm going to keep drawing until I get an ace. Well, the probabilities will not be the same because when I draw the first card, my probability of getting an ace is 4 aces out of 52 cards. Assuming I don't get an ace, I'm going to draw again, then the probability for the second card is 4 out of only 51 cards in the deck. So the probabilities are not staying the same, so therefore it is not a geometric situation. But if we do have a situation that's geometric, we use this formula here to help us determine the probability of it happening on the 7th trial or the 6th trial. So for example, if I was looking at the Kobe Bryant, which remember he makes 84% of his free throws, and he misses 16%. So if I ask him, what is the probability of him making his 4th free throw? Meaning he missed the first 3, and he didn't make one until the very 4th one. Okay? So we would look at here and say, probability of failure is 16%. So 16%, 0.16, to the number of free throws he's going to miss. He would miss 3 times his probability of success, 0.84, when he finally made his 4th free throw. And we would grab a calculator and see what that comes out to be. And that would be his probability of missing the first 3 and then making the 4th one. So that's what this formula is and how you interpret that. Okay, so here's an example called the birthday game. Not everyone knows this, but let's assume that for a second that one of my friends knows what day of the week he or she was born on. Okay, you're going to try to guess what that day of the week is. So whatever that day was, Monday, Tuesday, Wednesday, or Thursday, I know what the answer is. You're going to keep guessing, and I'm going to tell you whether you're right or wrong. So first of all, is this a geometric situation? So first of all, you got to check for the binary, and yes, either you're going to be correct, you have the right day, or you're going to be incorrect. The result of one student's guess has no effect on the result of another guess. So assuming that not everyone's in the same room, you enter the room one at a time, you make your guess and leave, your probability of success is not going to be any different. Now, obviously, that wouldn't be true if you were in the same room because you could hear what everybody else is guessing, and then you would know what answers not to pick. But assuming you're not in the same room when you're guessing, the results will be independent. We're going to count until we get the first correct guess. So we're going to keep going until someone gets it right. And the probability of any correct guess at any one time, again, not assuming everybody's in the room listening to everybody's guesses, would be 1 out of 7. So if we wanted to figure out what was the probability of them guessing it on the very first try, it would be 1 out of 7. If we wanted to figure out what the probability of getting on the second try, it means they got it wrong the first time, 6 out of 7. Then they got it right in the second time, 1 out of 7. And that comes out to be about 12%, as you can see here. If I waited till the third try, it means he got it wrong the first 2 times, so 6 out of 7 times 6 out of 7. And he finally got it right. You finally got it right on the third trial, 1 out of 7. And that comes out about 10.5% of the time. So if you can see, there's a pattern there. It's the number of failures times the final success. And hence, this is the formula that we use for geometric situations. Right there. Okay, so 1 minus p is the probability of failure. 1 less than whatever result we're looking for, times we finally hit the success on the trial that we're looking for. If we were to graph a probability distribution of a geometric situation, we would get something very similar to this, where the probability of getting on the first attempt might be 1 out of 7.143. Probably getting right on the second try, and this is again based on the birthday problem, was 12.2%. The third try was 10.5, etc. You notice it's ... here because it could conceivably go on forever. Again, assuming we're not in the same room and students aren't listening to everybody else's results, it could literally go on forever. If everybody comes in and keeps guessing Monday and that wasn't the right day, it could go on for a very long time. So that's what the ... is. But if you notice, this graph here is very, very skewed right, and that's because the most likely outcome is you're going to get it on the first or second or third guesses, and you're going to have times when it will take them 14 or 15 guesses, but they're not going to occur as often. So it's very sharply skewed to the right. The formula to help us get this, the mean, is a very simple formula. It's 1 divided by the probability of success. So in this situation here, we're trying to guess the day of the week that my friend's birthday is. It would be 1 divided by 1/7, which you remember from your fractions. We multiply by the reciprocal, so that's 1 times 7 over 1. We don't like to divide by fractions, we multiply by the reciprocal. So the mean here would be 7. We would expect on the average it will take 7 guesses before the students get it right. So a couple formulas to be aware of if we want the geometric mean and standard deviation. As I mentioned, the mean is 1 over p, or 1 over the probability of success. And the variance is 1 minus p divided by p squared, which again, 1 minus p is the probability of failure, p is the probability of success, and then we have to square root that to get the standard deviation. And again, these are formulas that are listed on your formula sheet, and you get to use them anytime you want. So it's not necessary to memorize them, but you do need to know that these two formulas are associated with geometric situations, not binomial and not other situations that we're going to look at later on. Okay, so continue to add these notes to the worksheet provided, and have a great night.